Good morning/afternoon, everyone. I'm excited to welcome you to today's presentation. We will be exploring the fascinating world of CD technology. My name is Aparna, and I am an assistant professor in the Department of Computer Science and Engineering at Swami Vivekananda Institute of Science and Technology. In this session, we'll cover the core concepts of CD technology, its applications, and how it's shaping the future of computing. Let's get started. Let's take a closer look at Chapter 11, which covers multimedia principles. In this chapter, we explore how different forms of media can be effectively used to enhance learning and communication. The focus is on understanding the core principles that guide the design of multimedia content. By applying these principles, we can create more engaging and effective educational materials. Specifically, this chapter delves into how to combine text, images, audio, and video in ways that support the learner's experience. It's all about making sure that the multimedia elements work together harmoniously to improve understanding and retention. This chapter is key to understanding how to leverage technology and multimedia tools to optimize learning environments. Let's take a closer look at the merits of CD technology. One of the major advantages is the ease of use and durability of the media itself. Unlike other storage options, CDs are quite robust and can handle regular handling without much issue. They also offer random access capability, meaning you can jump directly to any part of the data without having to go through everything sequentially, which is a significant improvement over tapes. Another key benefit is the high storage volume that CDs can provide. This makes them ideal for storing large amounts of data, whether it's software, music, or movies. Importantly, data stored on CDs isn't affected by electrical or magnetic fields, so it's more stable and less prone to corruption from electromagnetic interference. Plus, CDs don't require much maintenance or special handling, making them convenient for everyday use. The permanence of data on CDs is especially valuable when distributing error-free software or media like music and movies. This stability ensures that what you get is exactly what was intended, with minimal risk of data degradation over time. Now, moving on to the demerits. While CDs have many strengths, their access speed is slower compared to hard disks, which can be a limitation for certain applications that require quick data retrieval. Additionally, the efficiency of reading or writing data can be impacted if the RW head gets dirty or if there are scratches on the media. Even minor damage can cause read errors. It's also worth noting that standard CD-ROMs don't have the capability to write data, which limits their flexibility. For writable options like CDR and CDRW, portability becomes somewhat reduced because they are more delicate and can be more easily damaged compared to regular CDs. Overall, understanding these merits and demerits helps us see where CD technology fits best and how it compares to other storage options in terms of performance and durability. Let's take a closer look at the physical construction of a CD. It consists of a polycarbonate disc, which is 120 millimeters in diameter and about 1.2 millimeters thick. This polycarbonate layer is where the data is stored, and it contains tiny lands and pits. The pits are quite small, about 100 nanometers deep and 500 nanometers wide, and these are essential for encoding information. On top of the polycarbonate substrate, there's a reflective layer made of aluminum or gold. This layer plays a crucial role in reflecting the laser beam back to the sensor, allowing the data to be read accurately. To protect this reflective surface from oxidation and damage, a layer of lacquer is applied over it. All these elements work together to ensure the CD's durability and functionality. This physical construction is fundamental because it underpins how data is stored, protected, and ultimately retrieved during playback. Understanding this helps us appreciate the engineering behind what might seem like a simple disk, but is actually a highly precise data storage medium. Let's take a closer look at how CD technology actually works. The core principle involves a laser beam being focused onto the disk. When the laser hits the disk, it penetrates through the protective plastic layer and reaches a reflective layer underneath. Now, this is where the magic begins. If the laser hits a pit, the light gets scattered in different directions, making it harder for the detector to pick up a clear reflection. But if it hits a land, which is a flat area, the light is reflected directly back to the detector without scattering. This difference in reflection is crucial because it allows us to distinguish between a 1 and a 0. Each time the laser hits a pit or land, the reflected light causes a small electrical voltage in a light-sensing diode. These tiny voltages are then converted into a stream of binary data, 1s and 0s, that the computer can interpret. So, in essence, the laser's interaction with the disk's surface, whether it hits a pit or a land, forms the foundation of how data is read from a CD. This process is what makes CD technology reliable and efficient for data storage and retrieval. Let's take a closer look at CD technology and its principle of operation. CD technology, or compact disc technology, revolutionized how we store and access digital information. Its core principle revolves around encoding data onto a disk through tiny pits and lands that represent binary information. When you insert a CD into a player, a laser beam scans the surface, reading these variations. The laser detects changes in reflectivity caused by the pits and lands, converting these optical signals into electrical signals that the device can interpret as digital data. This process is highly precise, allowing for reliable storage and retrieval of large amounts of information. Understanding this principle is fundamental because it highlights how optical storage media like CDs paved the way for modern digital data handling. Throughout this chapter, we'll see how these basic principles underpin many of the technologies we rely on today. Let's take a closer look at CAV technology. Magnetic disks store data in concentric circles called tracks, and these tracks are divided into sectors. One important point to remember is that the amount of data stored in a smaller inner circle is less than that in the outer circles. This leads to some space wastage, which is a common challenge in disk storage. Now, when the disk spins, it does so at a constant angular velocity, or CAV. This means that every part of the disk, whether near the center or the edge, rotates at the same angular speed. But here's the interesting part. Because the outer sectors are larger, they actually move past the read-write head faster in terms of linear distance. This results in a higher linear velocity at the outer edge compared to the inner part. And because the sectors on the outer edge are bigger, the data transfer rate remains consistent across the entire disk. So, even though the speed at which data passes the head varies, the overall transfer rate stays constant, which is a key advantage of CAV technology. This understanding helps us see how disk design impacts performance and efficiency, an important aspect as we explore different storage technologies. Let's talk about CD technology and the concept of CLV, or constant linear velocity. Unlike older storage methods that used multiple concentric tracks, a CD-ROM stores data in a single spiral track that starts at the center and winds outward to the edge. This design helps improve storage efficiency because the data is all contained in one continuous path. Now, even though each sector on the disk is the same physical size, this creates an interesting challenge. The outer sectors move faster past the read-write head compared to the inner sectors, simply because of their position on the spiral. To handle this, the disk's rotation is slowed down when the read-write head is near the outer edge. This adjustment keeps the data transfer rate constant across the entire disk, ensuring smooth and reliable data reading or writing. This approach, called constant linear velocity, is essential because it balances the speed differences caused by the spiral format. It's a clever way to optimize performance and maintain data consistency, which is a key aspect of CD technology and helps us understand how data storage evolved to become more efficient and user-friendly. Let's take a closer look at how compact discs, or CDs, are constructed, starting from the very beginning. CDs are made from a round wafer of polycarbonate material, measuring about 120 millimeters in diameter and 1.2 millimeters thick. The first step in the process is creating a master, which is essentially the original data source. This master contains an image composed of 1s and 0s that represent the digital information we want on the disk. Next, a high-powered laser etches this data onto the master by creating microscopic pits, tiny indentations, that encode the information. These pits are crucial because they are what the laser readers will interpret later when you play the CD. Once the master is ready, it's used to produce master stamps. These stamps serve as molds for mass production. During manufacturing, the actual CDs are created by pressing them with these master stamps. This process duplicates the pattern of pits in exactly the right places, ensuring the data is accurately transferred. After stamping, the entire disc is coated with a thin layer of aluminum, which helps reflect the laser light during playback, and then sealed with a clear plastic layer to protect the surface. Finally, a printed label is applied, giving the CD its final appearance. This entire process highlights how technology allows us to reliably store and reproduce vast amounts of digital data in a compact, durable format. It's a fascinating blend of precision engineering and material science, all working together to bring our digital media to life. Let's talk about data encoding on compact discs. Unlike magnetic storage, CDs use a physical recording technique. When you start with a brand new disc, it's completely flat. Now, within the data area, the disc has two types of regions, lands and pits. Lands are simply flat areas, while pits are tiny imprints burned into the disc by a laser during manufacturing. As the disc spins, the laser rapidly moves over these regions, crossing from lands to pits and back many thousands of times each second. These transitions between flat and burned areas are critical because they encode the data. Specifically, when the laser moves from a land to a pit or vice versa, the system interprets that as a binary, 1. Conversely, if there's no transition, meaning the laser sees the same type of region continuously, it represents a 0. This physical encoding method allows data to be stored and read accurately by the laser, making CDs a reliable medium for digital storage. So, understanding this transition-based system is key to grasping how optical data storage works at a fundamental level. Let's take a closer look at Chapter 11, which focuses on CD technology and formats. As you know, there are many types of data that can be stored on a CD, and because of that, there are different ways of organizing those zeros and ones on the disc. These different organization methods are what we refer to as CD formats. Now, the official standards for these formats are actually documented in what are called colored books, each named after a color. For example, the red book contains the specifications for CD digital audio, which is what we commonly think of as standard music CDs. The yellow book, on the other hand, defines the standards for CD-ROM digital data and the extended architecture, known as CD-ROM XA. Moving on, the green book covers the specifications for CD Interactive, or CDI, which was designed for multimedia applications. The orange book is quite versatile. It includes standards for magneto-optical discs, CD recordable, and CD rewritable formats. These are the formats that allow you to record and rewrite data multiple times. Lastly, the white book sets the standards for photo CD and video CD, enabling high-quality images and video content. Understanding these different formats is key because they highlight how versatile CDs are as storage media. Each format serves a specific purpose, whether it's audio, data, multimedia, or recordable media. Recognizing these distinctions helps us appreciate the evolution and capabilities of CD technology as part of the broader digital storage landscape. Now, let's take a closer look at CD technology, specifically CDDA, which is the standard format for audio CDs. CDDA stands for Compact Disc Digital Audio, and it was established by the Red Book standard, developed by Philips and Sony back in 1980. This format has become the foundation for how we store and listen to digital audio on CDs. In terms of technical details, CDDA uses a sampling rate of 44.1 kHz, meaning it captures 44,100 samples per second, with a bit depth of 16 bits, providing good sound quality. It also records in stereo mode, which means it captures both left and right channels to give a rich, immersive sound experience. When audio data is stored on a CD, it's organized in blocks. Each block contains 2,352 bytes of data, and the CD plays back 75 of these blocks every second. This structured approach ensures consistent playback and data integrity. If you do the math for a standard 74-minute CD, the total storage capacity comes out to approximately 747 MB. That's quite efficient given the high quality of audio it maintains. Additionally, with the help of software called rippers, you can extract the digitally encoded audio data from CDs and convert it into common computer sound formats like WAV files. This process allows us to digitize and manipulate audio easily on our computers, connecting the physical medium of the CD to digital audio workstations or other software tools. Understanding CDDA is fundamental because it laid the groundwork for digital audio technology as we know it today, and it still influences how we handle audio data across various media. Let's take a closer look at CD technologies, starting with the CD-ROM. This standard was defined in the Yellow Book, which was published by Philips and Sony back in 1983. It's also known as the Data CD standard. Now, within this standard, there are two main modes that are used for storing data. The first one is Mode 1. In this mode, the data layout is quite similar to the audio CD format, or CDDA, but with a key difference. Instead of just storing audio samples, each block contains 2048 bytes of data. The remaining bytes in each block are dedicated to error detection and correction, which is crucial for maintaining data integrity. Now, if we think about how much data this setup can hold, assuming a typical read rate of 75 blocks per second on a 74-minute disk, we get a total capacity of roughly 650 megabytes. To put that into perspective, that's quite a substantial amount of data for that time. As for the data transfer rate, when reading at 75 blocks per second, we're transferring about 150 kilobytes per second. This speed is often referred to as 1x speed, which was the standard for early CD drives. So, in essence, the CD-ROM standard laid the groundwork for how we store and read digital data on optical disks, with clear specifications for data layout, error correction, capacity, and transfer speed. This standard really helped shape the development of data storage technology that we rely on today. Let's talk about CD technology, specifically CD-ROMs. Now, in Mode 2, it's quite similar to Mode 1, but the key difference is that error detection and correction codes are left out. This makes Mode 2 suitable for storing non-textual data like images, graphics, and videos, which don't need the same level of data integrity as text files. Because of this, the capacity of a CD in Mode 2 is calculated differently. Here, the total capacity is around 741 MB, derived from multiplying 2336 sectors per track, 75 tracks, 60 minutes per track, and 74 sectors per minute. Another important point is that a data CD contains a table of contents, or TOC, on the disk itself. This TOC functions similarly to the FAT, or File Allocation Table, on hard disks. It essentially lists what data is stored on the disk and where to find each file, making data retrieval more efficient. So, in summary, Mode 2 is optimized for multimedia storage, where high data integrity isn't as critical, and the TOC plays a vital role in organizing and locating data on the CD. This understanding helps us appreciate how CD technology adapts to different types of data storage needs. Thank you so much for your time and attention today. I really appreciate it. I hope this presentation has given you some valuable insights and practical ideas to take away. Remember, the key points we discussed, whether it's about innovative strategies, teamwork, or continuous improvement, are all connected to the bigger picture of achieving our goals. Your engagement and willingness to explore these concepts are what truly make a difference. So, once again, thank you for being part of this discussion. I look forward to seeing how you apply these ideas moving forward.